Hello there, and welcome to Sleepless Science Night. I'm so glad you found your way here tonight. The galaxy we call home stretches across the darkness like a river of ancient light, holding billions of stars and countless mysteries. Tonight, we'll drift gently through the Milky Way, exploring the strange and beautiful truths about our cosmic neighborhood. Wherever you are right now, perhaps lying in the quiet darkness of your room, or watching the night through your window, allow yourself to settle into this shared moment of stillness. Tonight, we'll explore 100 remarkable truths about the Milky Way galaxy. From the supermassive black hole at its center, to the spiral arms where new stars are born, to our own small corner orbiting quietly in the cosmic suburbs. If this quiet exploration of the cosmos helps you unwind, a gentle like and subscribe helps other stargazers find their way here too. It only takes a moment, but it means the universe to us, one sleepy soul at a time. For now, just let your shoulders soften, let your breathing fall into its own rhythm. Imagine yourself drifting through the gentle spiral of our galaxy, moving without effort through fields of distant stars. Close your eyes and take a deep breath. Imagine you're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through infinite space. The Milky Way is a barred spiral galaxy containing between 100 and 400 billion stars. Our galaxy earned its name from ancient observers who saw a milky band of light stretching across the night sky. Not realizing they were looking at billions of stars so distant, they blended together. The galaxy is roughly 100,000 light-years in diameter, meaning light traveling at 186,000 miles per second would take 100,000 years to cross from one edge to the other. Within this vast spiral, our Sun is just one ordinary star among hundreds of billions, orbiting the galactic center at a distance of about 26,000 light-years. The sheer scale of our galactic home challenges our ability to truly comprehend it. Yet here we are, tiny observers on a small planet, looking out and beginning to understand. At the center of the Milky Way lies a supermassive black hole called Sagittarius A star, pronounced Sagittarius A star. This cosmic monster has a mass equivalent to about 4 million suns, all compressed into a region smaller than our solar system. Despite its enormous mass, we cannot see Sagittarius A star directly because nothing, not even light, can escape its gravitational pull. Scientists confirmed its existence by observing stars orbiting at incredible speeds around what appears to be empty space, moving so fast that they complete an orbit in just 16 years, compared to our Sun's 230 million year orbit around the galaxy. The black hole sits there in the galactic center, neither creating nor destroying the galaxy, simply existing as the gravitational anchor around which 100 billion stars slowly turn. Our solar system orbits the Milky Way's center at approximately 514,000 miles per hour, or about 230 kilometers per second. Even at this incredible speed, it takes our Sun roughly 230 million years to complete one full orbit around the galaxy. This journey is called a cosmic year or galactic year. Since Earth formed about 4.5 billion years ago, our planet has completed only about 20 trips around the galaxy. When dinosaurs walked the Earth 230 million years ago, our solar system was on the opposite side of the Milky Way from where it is now. We are travelers through both space and time, moving through the galaxy on a journey that began before life itself emerged on our small world. The Milky Way is classified as a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of this bar. Our galaxy has 4 major spiral arms: the Perseus arm, the Norma arm, the Scutum Centaurus arm, and the Sagittarius arm. Our solar system resides in a minor arm called the Orion Spur, or the Orion Cygnus arm, a small branch connecting two of the major arms. The spiral arms are not permanent structures, but rather regions where stars, gas, and dust are compressed by gravitational forces, creating density waves that move through the galactic disk. New stars tend to form in these arms where material is compressed, which is why the arms appear brighter in photographs. We live in a relatively quiet suburban region of the galaxy, far from the intense stellar nurseries and crowded star clusters near the center. The Milky Way is approximately 13.6 billion years old, forming just 200 million years after the Big Bang. This makes our galaxy one of the older structures in the universe. The oldest known stars in the Milky Way, found in globular clusters orbiting the galactic center, are nearly as old as the galaxy itself. These ancient stars formed from the primordial hydrogen and helium created in the Big Bang, before heavier elements existed in abundance. By studying these elderly stars, astronomers can glimpse the conditions of the early universe. Our Sun, by comparison, is a relative newcomer at only 4.6 billion years old, born when the galaxy was already more than 9 billion years old. The Milky Way contains multiple generations of stars, each one enriching the galaxy with new elements. The Milky Way contains approximately 200 billion to 400 billion stars, though exact counts remain impossible due to dust clouds blocking our view. These stars come in many varieties: red dwarfs that burn slowly for trillions of years, massive blue giants that live fast and die young, and everything in between. Most stars in our galaxy are smaller and dimmer than our Sun, making them difficult to detect even with powerful telescopes. For every star visible to the naked eye on a clear night, there are millions more hidden in the depths of space, too distant or too dim for human eyes to perceive. The galaxy is far more populated than what we can see from our earthly vantage point. The Milky Way is moving through space at approximately 1.3 million miles per hour, relative to the cosmic microwave background radiation. This motion results from the combined gravitational pull of all nearby galaxies and galaxy clusters. Our galaxy isn't simply rotating in place, but traveling through the universe as part of a larger cosmic flow called the Great Attractor, a gravitational anomaly affecting the motion of galaxies over hundreds of millions of light years. We're simultaneously orbiting the Sun, which orbits the galaxy, which moves through space toward this mysterious attractor. Everything in the universe is in motion, from the smallest particles to the largest galaxy clusters, dancing through space in an intricate cosmic choreography that has continued for billions of years. The Milky Way's disk is incredibly thin compared to its width, measuring only about 1,000 light-years thick while spanning 100,000 light-years across. If you were to shrink the galaxy to the size of a dinner plate, its thickness would be comparable to a sheet of paper. This flat disk shape results from angular momentum and gravity working together. As the galaxy formed from a rotating cloud of gas billions of years ago, material collapsed toward the plane of rotation, flattening into the disk we observe today. The central bulge rises above and below this thin disk, containing older stars in more random orbits. Our solar system lies within this thin disk, giving us an edge on view when we look toward the galactic center, which is why the Milky Way appears as a band across our night sky. Between the stars of the Milky Way lies vast amounts of gas and dust called the interstellar medium, making up about 10 to 15% of the visible mass of the galactic disk. This material consists primarily of hydrogen gas, the most abundant element in the universe, along with trace amounts of heavier elements and tiny dust grains. The interstellar medium appears almost empty by Earth standards, with only about 1 atom per cubic centimeter in typical regions, compared to about 10 to the 19th power molecules per cubic centimeter in air at sea level. Despite this extreme thinness, the sheer volume of space between stars means this tenuous material adds up to billions of times the mass of our Sun. This gas and dust serves as the raw material from which new stars and planets form. The Milky Way is surrounded by a dark matter halo that extends far beyond the visible galaxy. This halo contains roughly 85 to 90% of the galaxy's total mass, about 10 times more mass than all the visible stars, gas, and dust combined. Dark matter is invisible material that doesn't emit, absorb, or reflect light, making it detectable only through its gravitational effects on visible matter. Scientists discovered dark matter's existence by observing that stars in the outer regions of galaxies orbit much faster than they should based on the visible mass alone. Something invisible must be providing additional gravitational pull. The nature of dark matter remains one of astronomy's greatest mysteries. The vast majority of our galaxy's mass consists of something we cannot see, cannot touch, and do not yet understand. The Milky Way is part of a small cluster of galaxies called the Local Group, which contains about 54 galaxies in total. The three largest members of the Local Group are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Most of the other galaxies in our local neighborhood are small dwarf galaxies orbiting around these three larger spirals like satellites orbiting planets. The entire Local Group spans about 10 million light-years across. Despite containing dozens of galaxies, the Local Group occupies a relatively small volume of space compared to the observable universe. Gravity binds these galaxies together, preventing them from being carried away by the expansion of the universe. We exist not in isolation, but as part of a gravitationally bound family of galaxies drifting through the cosmos together. The Milky Way is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor, located about 2.5 million light-years away. The two galaxies are approaching each other at approximately 250,000 miles per hour and will collide in about 4.5 billion years. When they merge, the collision will fundamentally reshape both galaxies, eventually forming a single elliptical galaxy that astronomers have nicknamed Milky. Despite the dramatic nature of this galactic collision, individual stars will rarely collide because the distances between stars are so vast. Our Sun and Solar System will likely survive the merger, though they may be flung into a different region of the combined galaxy. By the time this collision occurs, the Sun will already be nearing the end of its life. From Earth, we can only see about 6,000 to 8,000 stars with the naked eye under ideal dark sky conditions. Yet the Milky Way contains hundreds of billions of stars. The vast majority of our galaxy's stars are either too distant, too dim, or obscured by dust to be visible without telescopes. When you look at the night sky, you're seeing only the nearest and brightest stars in our cosmic neighborhood, all of them located within a few thousand light-years of Earth. The faint band of the Milky Way, visible on clear, dark nights, represents the combined light of billions of stars too distant to see individually, creating a soft glow across the sky. Most of our galaxy remains invisible to human eyes, hidden in the depths of space. The Milky Way's central bulge contains stars that are generally older, redder, and more tightly packed than stars in the disk. Near the galactic center, stars are separated by light weeks or light months, rather than the light years that separate stars in our neighborhood. If Earth orbited a star in the central bulge, the night sky would contain thousands of stars brighter than Venus appears from Earth. The density of stars in the core is roughly 1 million times greater than in our solar neighborhood. These crowded conditions make planetary systems in the galactic core less stable due to frequent gravitational interactions with passing stars. The galactic center is a fundamentally different environment from our quiet corner of the galaxy. The Milky Way produces approximately 3 new stars per year on average. This birth rate has slowed considerably since the galaxy's youth, when star formation occurred much more rapidly. New stars form in giant molecular clouds, vast regions of cold gas and dust that collapse under their own gravity. The most active star-forming regions in the Milky Way lie within the spiral arms, where gas compression triggers collapse and ignition. Each new star represents a conversion of simple hydrogen gas into a nuclear furnace that will shine for millions or billions of years. The Milky Way is still actively creating new stars. Though at a more measured pace than billions of years ago, the galaxy continues to renew itself, generation after generation, cycling matter from old stars into new ones. The Milky Way contains at least 100 billion planets, with potentially billions of Earth-like worlds in habitable zones around their stars. Statistical analysis suggests that nearly every star hosts at least one planet, and many stars have multiple planets. This means planets are far more common than we once imagined. Some of these worlds orbit in the habitable zone where liquid water could exist on the surface, a key ingredient for life as we know it. The sheer number of potentially habitable worlds in our galaxy raises profound questions about whether we are alone in the universe. Somewhere among the billions of stars, other worlds may be looking up at their own night skies. The Milky Way's spiral arms are not permanent structures, but rather density waves moving through the galactic disk. Similar to traffic jams on a highway, stars and gas clouds move in and out of the spiral arms as they orbit the galaxy. The arms appear bright because gas compressed in these density waves triggers intense star formation, and massive young stars shine brilliantly before dying quickly. By contrast, the space between spiral arms appears darker because fewer new stars are forming there. Our solar system passes through a spiral arm roughly every 100 million years during its orbit around the galaxy. Currently, we reside in a minor arm between two major spiral arms. The spiral pattern slowly rotates, creating an elegant structure that persists, even though individual stars constantly move through it. Globular clusters orbiting the Milky Way contain some of the oldest stars in the universe, with ages exceeding 13 billion years. These dense, spherical collections of stars contain hundreds of thousands to millions of stars, packed into regions only tens to hundreds of light years across. The Milky Way has about 150 to 200 known globular clusters, though more may exist hidden behind dust. These ancient stellar cities formed in the early universe when the galaxy was still assembling. The stars within them contain very few heavy elements because they formed before multiple generations of stellar nucleosynthesis had enriched the galaxy with metals. Globular clusters orbit the galactic center in elongated paths, often passing high above or below the main disk. They are fossils from the galaxy's youth. The Milky Way's rotation is not uniform. Different parts rotate at different speeds, a phenomenon called differential rotation. Stars closer to the galactic center complete their orbits faster than stars farther out, though the relationship is complex due to the distribution of dark matter. This differential rotation means that objects at different galactic radii gradually separate from each other over time. The Sun, located about 26,000 light-years from the center, takes roughly 230 million years to complete one orbit. Stars closer to the center orbit faster, while stars farther out orbit more slowly. This creates a spiral pattern that winds up over time. The rotation of the galaxy is one of the key observations that revealed the existence of dark matter, as visible matter alone cannot explain the observed rotation speeds. The interstellar medium in the Milky Way exists in several distinct phases, with dramatically different temperatures and densities. Cold molecular clouds can be as cool as 10 Kelvin, about -441 degrees Fahrenheit, while hot ionized gas in stellar blast waves can reach 10 million Kelvin. Between these extremes lie warm neutral and warm ionized phases. Each phase plays a different role in the galaxy's ecosystem. Cold clouds give birth to new stars, while hot gas carries energy from stellar explosions throughout the galaxy. The interstellar medium is not a uniform, static substance, but rather a complex, dynamic environment constantly stirred by stellar winds, supernova explosions, and gravitational interactions. The space between stars is far from empty and far from simple. Dust clouds in the Milky Way block visible light but allow longer wavelengths like infrared to pass through, which is why infrared astronomy has revolutionized our view of the galaxy. These dust clouds, made of tiny particles smaller than smoke particles, obscure large portions of the galactic disk when viewed in visible light. The dust is so effective at blocking light that we cannot see to the galactic center in optical wavelengths. However, infrared radiation, which has longer wavelengths, can penetrate these dust clouds, allowing astronomers to map regions previously hidden from view. This has revealed the true structure of the galaxy, including the central bar and the distribution of star-forming regions. Different wavelengths of light reveal different aspects of the same galaxy, each one adding pieces to our understanding. The Milky Way experiences periodic passages through the spiral arms, and some scientists suggest these passages might influence Earth's climate and mass extinction events. When the solar system moves through a spiral arm, it encounters denser regions of gas and dust, potentially altering the Sun's environment. Some researchers have proposed this could trigger comet impacts or changes in cosmic ray flux affecting Earth's climate. But this correlation remains highly speculative and is not supported by strong evidence. Most scientists do not accept this hypothesis. The connection between our galactic position and Earth's geological history is an interesting question still under investigation. Our planet's history may be influenced by our journey through the galaxy, though the specific mechanisms remain unclear. The Milky Way's magnetic field threads through the entire galaxy. Though it's about 100,000 times weaker than Earth's magnetic field, this galactic magnetic field plays a crucial role in star formation by providing support against gravitational collapse in molecular clouds. It also guides the motion of charged particles called cosmic rays as they travel through interstellar space. The field's structure is complex, with patterns that vary between the disk, bulge, and halo regions of the galaxy. Scientists are still working to fully map and understand the galactic magnetic field because it's difficult to observe directly. Despite its weakness, this invisible force field helps shape the structure and evolution of our galaxy over billions of years. The field is created and maintained by the combined motion of charged particles throughout the galaxy. The Milky Way is thought to have cannibalized several smaller galaxies throughout its history, absorbing them and incorporating their stars. Astronomers have discovered streams of stars in the outer halo that appear to be remnants of disrupted dwarf galaxies. These stellar streams mark the paths of smaller galaxies that were torn apart by the Milky Way's gravitational forces as they passed too close. The Sagittarius dwarf elliptical galaxy is currently being torn apart by our galaxy's gravity, with streams of its stars wrapping around the Milky Way. This galactic cannibalism is a natural process in galaxy evolution. Large galaxies grow over time by consuming smaller neighbors. Our galaxy's size and structure today results partly from these ancient mergers. The Milky Way rotates clockwise when viewed from above the North Galactic Pole, which lies in the constellation Coma Berenices. From our position within the galaxy, we see the galactic center toward the constellation Sagittarius. The plane of the Milky Way is tilted about 63 degrees relative to the plane of Earth's orbit around the Sun, which is why the Milky Way's band crosses the sky at an angle rather than following the ecliptic path of the planets. During certain times of year, particularly summer evenings in the Northern Hemisphere, the densest part of the Milky Way arcs high across the sky, offering spectacular views of the galactic center region. Our perspective from within the galaxy gives us a unique view, though it also makes it harder to understand the galaxy's overall structure. We see our home galaxy edge on as an insider rather than an external observer. And now, let's pause for just a moment. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronauts we send to the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. The Milky Way's central supermassive black hole, Sagittarius, a star, is relatively quiet compared to black holes in other galaxies. Many galaxies have active galactic nuclei where supermassive black holes actively consume surrounding material, releasing enormous amounts of energy. Our galaxy's central black hole consumes matter much more slowly, producing only occasional flares of radiation. Scientists have observed it swallowing gas clouds and occasionally flaring up, but most of the time it remains dormant. This relative quietness makes our galaxy more hospitable to life than galaxies with highly active centers. The black hole sits there, patient and nearly invisible, an anchor for 100 billion stars. Stars in the Milky Way come in 7 main spectral classes designated by letters: O, B, A, F, G, K, and M. These classes are arranged from hottest to coolest, with O-type stars burning at over 30,000 Kelvin and M-type stars at around 3,000 Kelvin. Our Sun is a G-type star, with a surface temperature of about 5,800 Kelvin, placing it in the middle range. The most common stars in the galaxy are M-type red dwarfs, making up about 75% of all stars. The rarest are massive O-type and B-type stars, which burn intensely but die young, often living only a few million years before exploding as supernovae. The Milky Way's disk contains distinct populations of stars with different ages and compositions, called Population 1 and Population 2 stars. Population 1 stars, like our Sun, are younger and metal-rich, containing heavier elements created by previous generations of stars. Population 2 stars are older, metal-poor, and found primarily in the galactic halo and bulge. The difference in chemical composition reveals the galaxy's history of stellar nucleosynthesis. Early generations of stars formed from nearly pure hydrogen and helium. When these stars died, they scattered heavier elements into space. Later generations incorporated these elements, becoming progressively richer in metals with each stellar cycle. The composition of a star serves as a timestamp, revealing when in the galaxy's history it formed. The Milky Way's halo extends far beyond the visible disk, possibly reaching 500,000 to 1 million light-years from the galactic center. This vast halo consists primarily of dark matter, with scattered stars, globular clusters, and satellite galaxies embedded within it. The halo is roughly spherical, enveloping the flattened disk like a vast, invisible bubble. Most of the galaxy's mass resides in this extended halo, yet it remains largely undetectable except through its gravitational effects. The boundary between the Milky Way and intergalactic space is not sharp but gradual, with the galaxy's influence fading slowly across hundreds of thousands of light-years. Our galaxy is much larger than the bright spiral we see in photographs. The Milky Way's stellar metallicity gradient shows that stars near the galactic center generally contain more heavy elements than stars in the outer disk. This gradient exists because star formation and stellar evolution have been more active in the inner galaxy, producing more heavy elements through nucleosynthesis. The outer regions, with lower star formation rates, have been less enriched. Our Sun's metallicity is higher than about 93% of stars in the galaxy, indicating we formed in a relatively enriched environment. The gradient provides clues about how the galaxy formed and evolved, suggesting that different regions have different histories. Chemical composition serves as a tracer of galactic evolution, written in the spectrum of light from each star. More than half of all stars in the Milky Way are thought to be part of binary or multiple star systems. In these systems, 2 or more stars orbit their common center of mass, bound together by gravity. Some binaries are so close their surfaces nearly touch, while others are separated by thousands of astronomical units. Binary stars can exchange mass, especially when one star expands into a red giant, potentially leading to dramatic events like novae or even supernovae. Planetary systems around binary stars would experience complex gravitational environments and unusual patterns of day and night. Many stars in our galaxy do not travel alone through space, but have stellar companions. The Milky Way's disk shows a subtle warp, particularly in its outer regions, where the disk bends above and below the main galactic plane. This warping might result from gravitational interactions with satellite galaxies or from the torque exerted by the galaxy's dark matter halo. Similar warps appear in many spiral galaxies, suggesting common formation mechanisms. The warp in our galaxy makes the disk resemble the brim of a warped hat rather than a perfectly flat disk. From our position within the galaxy, this warp is difficult to detect directly, but mapping the distribution of gas and stars throughout the disk reveals the distortion. The galaxy is not a perfect geometric structure, but a dynamic, slightly irregular system. Stellar winds from massive stars and supernova explosions create enormous bubbles in the interstellar medium called superbubbles. These structures can be hundreds of light years across, filled with hot, low-density gas cleared away by the energy of stellar explosions. Our solar system actually resides within one such structure called the local bubble, a region of lower density gas extending about 300 to 1,000 light years across. The local bubble was likely created by multiple supernovae over the past 10 to 20 million years. These explosions swept away much of the interstellar gas, creating the relatively empty region we now inhabit. The bubble provides a clear view of distant stars by reducing intervening dust. The Milky Way contains thousands of stellar nurseries, regions where new stars are actively forming from collapsing gas clouds. Some of the most famous include the Orion Nebula, located about 1,350 light-years away, where hundreds of new stars are being born. These nurseries typically hide within dark molecular clouds, invisible at optical wavelengths, but bright in infrared. The process of star formation takes millions of years, beginning when a region of gas becomes dense enough that gravity overcomes the pressure supporting it. As the cloud collapses, it fragments into smaller clumps, each potentially forming a star or multiple stars. The galaxy continually renews itself through this process, converting diffuse gas into concentrated stellar furnaces. The Milky Way's rotation curve, a graph showing orbital speed versus distance from the center, provided key evidence for dark matter's existence. According to visible mass alone, stars far from the galactic center should orbit much more slowly than observed. Instead, orbital speeds remain roughly constant even at large distances, indicating the presence of additional unseen mass. This flat rotation curve cannot be explained by visible matter and requires a massive dark matter halo. Similar rotation curves in other galaxies provided converging evidence for dark matter, transforming our understanding of galactic structure and the universe's composition. Something invisible outweighs everything we can see by a factor of 10 to 1. Wolf-Rayet stars in the Milky Way are massive stars nearing the end of their lives, shedding their outer layers in powerful stellar winds. These rare objects have surface temperatures exceeding 30,000 Kelvin and lose mass at extraordinary rates, sometimes expelling an Earth mass worth of material every few thousand years. The intense stellar winds create beautiful nebulae around these dying stars. Wolf-Rayet stars represent a brief phase in massive stellar evolution, typically lasting only a few 100,000 years before the star explodes as a supernova. Despite their rarity, only a few thousand exist in the entire galaxy. They play an important role in enriching the interstellar medium with heavy elements. They are among the most energetic single stars in the galaxy. The Milky Way's bulge has a boxy or peanut-shaped structure when viewed edge-on, rather than being perfectly spherical. This unusual shape results from the vertical buckling of the central bar, which extends both above and below the galactic plane. The bulge contains both old stars from the galaxy's youth and some younger stars formed more recently. Its structure reveals the dynamic history of the inner galaxy, where gravitational interactions have shaped stellar orbits over billions of years. The bulge rotates as a solid body rather than showing the differential rotation seen in the disk. This distinct kinematic behavior further distinguishes it from the disk population. Central bulges are common features of spiral galaxies, marking regions of concentrated mass and stellar density. Approximately 50 satellite galaxies orbit the Milky Way, though the exact number changes as new discoveries are made. The largest of these satellites are the Large and Small Magellanic Clouds, visible from the southern hemisphere as diffuse patches of light. Most satellites are dwarf galaxies containing only millions to billions of stars, compared to our galaxy's hundreds of billions. These satellites orbit within the Milky Way's dark matter halo, bound by gravity. Some will eventually merge with the Milky Way, adding their stars to our galaxy. The satellites represent the remnants of galaxy formation, smaller structures that never grew to full galactic size. They provide laboratories for studying galaxy evolution and dark matter distribution. The Milky Way's disk contains a thin disk and a thick disk with different populations of stars. The thin disk, where our Sun resides, is younger and contains more metals, with stars orbiting in nearly circular paths close to the galactic plane. The thick disk contains older, metal-poor stars with more elongated orbits that carry them farther above and below the plane. The thick disk is thought to have formed through different processes, perhaps from the early galaxy's tumultuous assembly, or from satellite galaxies disrupted long ago. This vertical structure adds complexity to the galaxy's architecture. Not all stars orbit in the neat, flat patterns we might expect, but rather in a layered arrangement reflecting different formation epochs. Stellar remnants called white dwarfs, neutron stars, and black holes populate the Milky Way as the endpoints of stellar evolution. White dwarfs, the remnants of sun-like stars, number in the billions throughout the galaxy. Neutron stars, left behind by supernova explosions, spin rapidly and sometimes appear as pulsars when their beamed radiation sweeps past Earth. Stellar mass black holes, the collapsed cores of the most massive stars, may number 100 million or more in our galaxy, though most remain invisible. These stellar remnants represent the final states of stellar evolution, concentrating matter to extraordinary densities. Each one marks the death of a star and the birth of something strange and new. If you're still here, still awake, still drifting with us through these stories, take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. The Milky Way contains vast regions called H2 regions, pronounced H2, where ultraviolet radiation from hot young stars ionizes surrounding hydrogen gas. These regions glow with a characteristic pinkish-red light from ionized hydrogen atoms recombining with electrons and releasing photons. Famous examples include the Orion Nebula and the Eagle Nebula. H2 regions mark sites of recent star formation, where massive young stars illuminate their birthplace clouds. The glowing gas reveals the presence of stellar nurseries hidden within dark molecular clouds. These regions can be tens to hundreds of light years across, creating some of the most visually spectacular structures in the galaxy. They are temporary features, lasting only a few million years before the stars disperse. The local group, which includes the Milky Way, spans about 10 million light-years and contains approximately 54 galaxies. This represents a small gravitationally bound cluster in the universe. Beyond the local group lie other galaxy groups and massive galaxy clusters, each containing hundreds to thousands of galaxies. The local group is moving through space at about 1.3 million miles per hour toward a region called the Great Attractor. All these structures participate in the cosmic web, a large-scale pattern of galaxy clusters and voids stretching across the observable universe. Our galactic neighborhood is one small node in this vast cosmic network. The Milky Way's stellar halo contains fast-moving stars called hypervelocity stars, traveling at speeds sufficient to escape the galaxy's gravitational pull. These stars were likely accelerated by close encounters with the supermassive black hole at the galactic center, or through interactions in binary systems. Some hypervelocity stars move at over 1,000 kilometers per second, fast enough to leave the Milky Way entirely and enter intergalactic space. Their unusual velocities make them rare and valuable for studying extreme gravitational interactions. These stellar wanderers are being ejected from their home galaxy, destined to travel alone through the void between galaxies. Each one carries with it the story of a dramatic encounter near the galactic center. Cosmic rays, high-energy particles traveling through the galaxy at nearly the speed of light, originate partly from supernova remnants within the Milky Way. These particles, mostly protons and atomic nuclei, carry enormous energies and can penetrate spacecraft and even Earth's atmosphere. When they strike the atmosphere, they create cascades of secondary particles detectable at ground level. The galactic magnetic field deflects cosmic rays, making their paths curve through space rather than traveling in straight lines. Some cosmic rays have energies exceeding anything achievable in human-made particle accelerators. They represent natural high-energy physics experiments occurring throughout the galaxy. The Milky Way's bar, a dense structure of stars extending through the galactic center, measures roughly 27,000 light-years long. This bar rotates as a unit, influencing the orbits of stars and gas throughout the inner galaxy. Bars are common in spiral galaxies, appearing in about 2/3 of disk galaxies in the universe. The bar channels gas toward the galactic center, potentially feeding the central black hole and triggering star formation in the nucleus. Our solar system lies far enough from the bar that its influence on our orbit is minimal. The bar gives the Milky Way its classification as a barred spiral, rather than a pure spiral galaxy. Pulsar timing observations across the Milky Way have created a galactic scale detector for gravitational waves. Pulsars act like cosmic clocks, emitting radio pulses with extraordinary regularity. Gravitational waves passing through space cause tiny changes in the distances between Earth and distant pulsars, slightly altering pulse arrival times. By monitoring many pulsars simultaneously, astronomers can detect gravitational waves from supermassive black hole mergers in distant galaxies. This technique turns the entire galaxy into an experiment, using nature's most precise clocks to sense ripples in space-time itself. The galaxy becomes both observatory and observed. The metallicity of the interstellar medium in the Milky Way is approximately twice the Sun's metallicity in the inner regions and decreases toward the outer disk. This gradient reflects the history of star formation and element production across the galaxy. Regions with more active star formation have cycled material through more stellar generations, enriching the gas. The Sun's metallicity represents conditions 4.6 billion years ago when it formed. Today's interstellar medium has been further enriched. Over cosmic time, the galaxy's overall metallicity has increased as successive generations of stars have manufactured and dispersed heavy elements. The universe is gradually becoming more chemically complex. Star clusters in the Milky Way come in two main types: open clusters and globular clusters. Open clusters are young, loosely bound groups containing tens to thousands of stars, typically found in the galactic disk. Globular clusters are ancient, tightly bound spheres of hundreds of thousands of stars, orbiting in the halo. The Pleiades is a famous open cluster visible to the naked eye, while Omega Centauri is among the largest globular clusters. Open clusters disperse over time, their stars drifting apart. Globular clusters remain bound for billions of years. Each type reveals different aspects of stellar birth and galactic structure. The Milky Way's disk-scale height, the vertical thickness of the stellar distribution, varies for different stellar populations. Young, massive stars hug tightly to the midplane with scale heights of only 50 to 100 light-years. Older stars have larger scale heights, reaching 300 to 1,000 light-years or more. This vertical structure arises because older stars have had more time to be gravitationally perturbed by molecular clouds and spiral arms, gaining vertical motion. The youngest stars mark the current plane of star formation. Older stars trace the galaxy's history, their vertical distribution recording billions of years of gravitational interactions. The disk is layered like an archaeological site, with age increasing upward. Stellar streams in the Milky Way's halo mark the remains of satellite galaxies and globular clusters torn apart by tidal forces. These streams appear as arc-like patterns of stars sharing similar orbits and chemical compositions. The Sagittarius stream wraps around the entire galaxy, tracing the disruption of the Sagittarius dwarf elliptical galaxy. As satellites orbit the Milky Way, its stronger gravity stretches them along their orbital path until they dissolve completely. These streams map the accretion history of our galaxy, showing how it has grown by consuming smaller neighbors. They are like rivers of stars, flowing through the halo, slowly fading as they merge with the galactic background. We've traveled halfway, and in this moment, let each breath guide you to realize time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. And we continue drifting. The Fermi bubbles are enormous structures extending 25,000 light-years above and below the Milky Way's center. These bubbles emit gamma rays and appear as giant lobes of hot plasma. They likely formed from a burst of activity from the central supermassive black hole several million years ago, or from intense star formation in the galactic center. The bubbles continue expanding outward at approximately 2 million miles per hour. From inside the galaxy, we see them as diffuse features in the gamma-ray sky. They reveal that our galaxy's center was far more active in the recent past. Variable stars in the Milky Way pulsate with regular periods that depend on their intrinsic brightness. Cepheid variables, a particular type, have been crucial for measuring cosmic distances. Their period luminosity relationship means we can determine their true brightness by measuring their pulsation period, then calculate their distance by comparing true brightness to observed brightness. This technique helped establish the scale of the universe and revealed that other galaxies exist beyond the Milky Way. Variable stars serve as standard candles, allowing astronomers to map the three-dimensional structure of our galaxy and measure distances to others. They illuminate the cosmic distance ladder. Counting the Milky Way's stars precisely remains impossible because most are too faint to detect individually, and dust obscures large portions of the galaxy. Astronomers estimate by measuring the galaxy's total luminosity and mass, then using models of stellar populations. The smallest red dwarf stars far outnumber all other types, yet contribute little to the galaxy's light. Many of the galaxy's stars remain invisible in even our most sensitive surveys. The actual number of stars in our galaxy may never be known with perfect precision, though current estimates place it somewhere between 100 and 400 billion. Molecular clouds in the Milky Way are the coldest and densest structures in the interstellar medium. These dark clouds, invisible at optical wavelengths, have temperatures as low as 10 Kelvin and densities thousands of times greater than typical interstellar gas. They contain mostly hydrogen molecules along with carbon monoxide and complex organic molecules. Within these clouds, gravity can overcome thermal pressure, allowing collapse and star formation. The largest molecular clouds contain enough mass to form millions of stars. They are stellar nurseries, incubators, where new solar systems come into being, shrouded in darkness until newborn stars illuminate them from within. The Milky Way experiences approximately 2 to 3 supernovae per century on average. These remarkable stellar transformations briefly outshine entire galaxies, releasing immense energy in moments. Supernovae gently enrich the interstellar medium with heavy elements and encourage new episodes of star formation through their spreading waves. The last supernova visible to the naked eye in our galaxy occurred in 1604, observed by Johannes Kepler. We're statistically overdue for another. When the next one occurs, it may be visible in daytime, a cosmic event marking the death of a massive star and the birth of a neutron star or black hole. The Sun orbits the galactic center with a velocity of approximately 230 kilometers per second, or about 514,000 miles per hour. Despite this tremendous speed, we don't feel it because everything in our local environment moves together. The Sun drags its family of planets along, maintaining their orbits as the entire solar system circles the galaxy. This motion is perpendicular to Earth's orbital motion around the Sun and to Earth's rotation. We exist in multiple simultaneous motions, spiraling through space on overlapping cosmic merry-go-rounds, yet experience only the gentle pull of Earth's gravity. The Milky Way's neutral hydrogen extends far beyond the visible stellar disk, forming an extended H1 disk. This gas disk contains roughly 10% of the galaxy's baryonic mass and provides raw material for future star formation. The H1 layer is thinner and more uniform than the molecular gas distribution. Studying its structure reveals the galaxy's rotation curve and total mass distribution. The extended H1 disk also shows evidence of interactions with satellite galaxies, appearing disturbed and warped in outer regions. This diffuse hydrogen represents the reservoir from which stars will continue forming for billions of years to come. Blue straggler stars in the Milky Way appear younger than they should be, defying expectations based on their cluster environments. These stars are bluer and more massive than other cluster members, suggesting youth, yet they reside in ancient clusters where all stars should have aged similarly. Blue stragglers likely form through stellar collisions in dense cluster cores or through mass transfer in close binary systems. Their existence reveals that stellar evolution is not always a solitary process. Some stars receive fresh fuel through interactions with companions, effectively resetting their evolutionary clocks. The Milky Way contains approximately 100 to 200 globular clusters, ancient spherical collections of stars. These dense clusters orbit the galaxy in elongated paths, spending most of their time in the halo far above and below the disk. Each globular cluster contains between 100,000 and several million stars, packed into regions only 100 to 200 light-years across. At their cores, stars are separated by light weeks rather than light-years. If Earth orbited a star in a globular cluster core, the night sky would contain thousands of stars brighter than Venus. These clusters are among the oldest objects in the galaxy, fossils from its formation epoch. The Gould Belt is a ring of young stars and star-forming regions tilted about 20 degrees from the galactic plane. This local structure extends about 3,000 light-years across and includes many familiar bright stars and nebulae. The Orion and Taurus star-forming regions are part of the Gould Belt. Its origin remains debated, perhaps formed by a supernova shockwave or satellite galaxy interaction millions of years ago. The belt surrounds our solar system, placing us near the edge of this relatively recent burst of star formation in our galactic neighborhood. The Milky Way's magnetic field strength varies from region to region, but averages about 6 microgauss. For comparison, Earth's magnetic field is about 500,000 microgauss. Despite its weakness, the galactic field influences cosmic ray propagation, star formation, and the behavior of interstellar gas. The field follows the spiral arm structure in the disk and has a more complex geometry in the halo. It's generated by the combined motions of charged particles throughout the galaxy, creating what's called a dynamo effect. This invisible force threads through every corner of the galaxy, shaping its structure over cosmic time. Planetary nebulae in the Milky Way mark the final stages of sun-like stars, expelled shells of gas illuminated by the dying star's core. These nebulae glow in beautiful colors from ionized gas, creating some of astronomy's most aesthetically pleasing images. The central star, a hot white dwarf, provides ultraviolet radiation that causes the surrounding gas to fluoresce. Planetary nebulae last only about 10,000 to 20,000 years before fading. A brief final display before the white dwarf cools into darkness. Our Sun will likely create a planetary nebula in about 5 billion years. The Sun's motion through the local standard of rest, the average motion of nearby stars, is called the peculiar velocity. Our Sun moves at about 12 kilometers per second relative to this local standard, drifting slowly toward the constellation Hercules. This peculiar motion results from gravitational perturbations accumulated over billions of years. Every star has its own peculiar velocity, each one slightly different from its neighbors. These small deviations from circular orbits tell stories of past encounters with molecular clouds, spiral arm passages, and gravitational interactions. The galaxy is not a machine with perfect circular gears, but a dynamic community where each star follows a slightly different path. The Milky Way's central parsec, a region about 3.26 light-years across surrounding Sagittarius, a star, contains a dense concentration of massive stars. These stars orbit the black hole in a challenging environment of intense radiation and tidal forces. Some complete orbits in just years or decades, their velocities reaching a significant fraction of light speed at closest approach. One star, S2, orbits the black hole every 16 years. Observing its motion provided some of the strongest evidence for the black hole's mass. These stars inhabit one of the most unusual environments in the galaxy. Stellar winds from hot stars create expanding bubbles in the interstellar medium, clearing regions of gas and dust. Massive O and B stars can create wind bubbles tens to hundreds of light-years across during their lifetimes. When these stars eventually explode as supernovae, they further excavate these regions, creating superbubbles. Multiple generations of massive stars in OB associations can create connected networks of bubbles and shells. These structures shape the appearance of the interstellar medium, creating the complex, foam-like structure visible in detailed images. Star formation is a dynamic process that powerfully reshapes its surroundings. The Milky Way's disk is not perfectly flat, but shows vertical oscillations as our solar system moves through it. These oscillations occur with a period of approximately 60 to 70 million years as we bob up and down through the galactic plane. Currently, we are located slightly above the midplane and moving toward it. These vertical motions result from gravitational perturbations by spiral arms and molecular clouds. Each passage through the dense midplane exposes the solar system to a higher density of stars and potential comet-disturbing encounters. Brown dwarfs in the Milky Way are substellar objects too massive to be planets, but too small to sustain hydrogen fusion. With masses between 13 and 80 Jupiter masses, they represent failed stars that never ignited. Brown dwarfs glow faintly from residual heat and, in more massive cases, from deuterium fusion. They are difficult to detect due to their low luminosity. Estimates suggest the galaxy contains billions of brown dwarfs, potentially outnumbering stars. These dim objects drift through space, neither truly stars nor planets, occupying a transitional realm in the cosmic census of objects. The Milky Way's oldest known star, discovered in the halo, has an age of approximately 13.5 billion years. This makes it nearly as old as the universe itself, forming just a few hundred million years after the Big Bang. Its extremely low metallicity confirms it belongs to one of the earliest generations of stars. Finding and studying these ancient stars provides glimpses into the primordial universe when the first stars were forming. They are time capsules, preserving in their atmospheres the chemical signature of the early cosmos when heavy elements were scarce. The local arm, or Orion's spur, where our solar system resides, is a minor spiral feature between two major arms. This structure extends roughly 3,500 light-years in radius and contains our local neighborhood of stars. While not a major arm, the Orion spur hosts active star formation, including the famous Orion and Carina nebulae. Our position in this minor arm gives us a relatively safe location, far from the crowded, high-radiation environment near the galactic center, yet with enough nearby structure to make the night sky interesting. X-ray binaries in the Milky Way consist of a normal star orbiting a compact object like a neutron star or black hole. As matter from the normal star accretes onto the compact object, it heats to millions of degrees and emits X-rays. These systems can outshine thousands of normal stars despite their small size. Some X-ray binaries are transient, flaring dramatically before fading. Others remain persistently bright. They represent laboratories for studying matter under intense gravity and magnetic fields. Each one marks a stellar transformation into an energetic binary system, sometimes dynamic and changing, always fascinating. The Milky Way's spiral structure is primarily defined by H2 regions, OB associations, and molecular clouds rather than old stars. Young, massive stars trace the current spiral pattern, while older stars have had time to drift away from their birth sites. The spiral arms are temporary compression waves moving through the disk, regions where gas is squeezed and star formation is triggered. As stars age, they move out of the spiral arms, making the arms appear as transient features highlighted by youth. The galaxy's appearance changes depending on what wavelength of light we observe. The Milky Way may contain billions of rogue planets, worlds ejected from their parent star systems and drifting through interstellar space. These lonely worlds were likely cast out during the chaotic early phases of planetary system formation, when gravitational interactions between planets were common. Some may have been ejected when their star passed too close to another star. Rogue planets are extremely difficult to detect because they emit no light of their own and reflect no starlight. They represent a hidden population of worlds wandering the galaxy alone, never seeing sunrise. The Milky Way's satellite galaxies are being tidally stripped of their stars, gradually dissolving into the galactic halo. This process is visible in real time for several satellites, including the Sagittarius dwarf galaxy. As satellites orbit, the Milky Way's differential gravity pulls harder on the near side than the far side, stretching the satellite along its orbit. Over many orbits, the satellite loses stars to tidal stripping until nothing remains but a dispersed stream. This represents galactic cannibalism in slow motion, the inevitable fate of small galaxies orbiting large ones. Runaway stars in the Milky Way move at exceptionally high velocities. often ejected from their birthplaces by gravitational interactions or supernova explosions. When a massive binary star system experiences a supernova, the surviving companion can be flung away at hundreds of kilometers per second. Other runaways result from multi-body interactions in dense star clusters. These fast-moving stars create bow shocks as they plow through the interstellar medium, visible in infrared images. Each runaway carries a story of dramatic disruption, traveling alone through the galaxy at speeds far exceeding typical stellar motions. The Milky Way's scale height increases with stellar age, creating a layered structure in the disk. Young stars remain close to the midplane with scale heights of 50 to 100 light-years. Intermediate age stars like the Sun have scale heights of 200 to 300 light-years. The oldest disk stars extend 1,000 light-years or more above and below the plane. This vertical age gradient results from cumulative gravitational scattering over billions of years. The disk is not uniform, but stratified by age, with each layer telling part of the galaxy's history. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. All are circles, cycles, endless orbits. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. The Milky Way continues to accrete gas from its surroundings, feeding future star formation, high-velocity clouds, masses of neutral hydrogen moving at anomalous velocities, rain down onto the galactic disk. These clouds may represent primordial gas falling into the galaxy or material ejected by past galactic activity returning. The infall provides fresh fuel, extending the galaxy's star-forming lifetime. Without this accretion, the Milky Way would consume its remaining gas in several billion years. Instead, the slow rain of external material sustains ongoing starbirth. The galaxy breathes in, preparing for future generations. The Sun will complete only about 20 to 25 more orbits around the Milky Way before it exhausts its nuclear fuel. Each orbit takes 230 million years, and the Sun has about 5 billion years remaining. This limited number of future galactic years reminds us of cosmic timescales. Even stars have lifetimes measured in cycles around the galaxy. Everything in the universe operates on schedules, some slow, some fast, all temporary. White dwarfs will eventually cool to become black dwarfs, theoretical stellar remnants that have radiated away all their heat. This cooling process requires longer than the current 13.8 billion year age of the universe, perhaps 10 to 100 trillion years. No black dwarfs yet exist anywhere. In the unimaginably distant future, when star formation has ceased and the last stars have died, the Milky Way will become a quiet realm of black holes and black dwarfs. All light is temporary. The galaxy's bright era is fleeting on the longest timescales. The Milky Way's luminosity totals approximately 26 billion times the Sun's luminosity. This combined light from hundreds of billions of stars creates the galaxy's overall brightness. Most of this luminosity comes from a relatively small number of massive, bright stars, rather than the abundant but dim red dwarfs. The galaxy shines across the electromagnetic spectrum, from radio waves through gamma rays. All that light, radiating into intergalactic space, marks our galaxy's presence in the cosmos. We are a glowing island in the dark. The Sun's position in the galaxy oscillates up and down through the disk with a period of 60 to 70 million years. We're currently about 75 light-years above the midplane, moving downward, At maximum displacement, we reach about 200 to 300 light-years above or below the plane. This oscillation results from the disk's gravitational pull, creating a vertical harmonic motion. Everything oscillates, bounces, returns. Motion pervades the universe at every scale. Magnetars in the Milky Way are neutron stars with magnetic fields billions of times stronger than Earth's. These rare objects have the strongest magnetic fields known in the universe. Their intense fields twist and crack the neutron star's crust, releasing enormous bursts of gamma rays and X-rays. Only about 30 magnetars are known in our galaxy, though more likely exist undetected. They represent the most unusual magnetic environments imaginable. Matter behaves strangely in such fields. Atoms stretched into elongated shapes. They are cosmic laboratories of intense physics. The Milky Way's total mass, measured by observing how satellite galaxies orbit, reaches approximately 1.5 trillion times the mass of our Sun. This vast halo of matter, both visible and invisible, extends far beyond the bright spiral we see in photographs. The gravitational pull of this enormous mass holds our galaxy together and shapes the orbits of everything within it, from individual stars to entire satellite galaxies. We live within something much more massive than appearances suggest. Most of reality remains hidden. The Milky Way's central black hole, Sagittarius A star, has been directly observed through very long baseline interferometry. Astronomers created an Earth-sized telescope by linking radio dishes worldwide, achieving resolution fine enough to image the black hole shadow. The image shows a ring of light surrounding darkness, light from heated gas orbiting just outside the event horizon. This confirmed the black hole's existence beyond doubt. We can now see the unseeable photograph, something from which light cannot escape. Science reveals the invisible. Our galaxy contains stellar fossils, stars preserving chemical signatures from the early universe. These ancient stars contain almost no elements heavier than helium, indicating they formed from nearly primordial gas. Their atmospheres hold clues about conditions in the first billion years after the Big Bang. By studying these living fossils, astronomers glimpse the universe's youth. Each old star is a message from the past, a record written in light and preserved for billions of years. The galaxy remembers its beginnings in the composition of its oldest stars. The Milky Way's disk shows spiral density waves propagating through it like ripples on water. These waves compress gas as they pass, triggering star formation and creating the spiral pattern. The waves move at a different speed than the stars, which orbit through them. Material enters a spiral arm from one side, gets compressed, forms stars, then exits on the other side. The pattern persists though material flows through it. Form and substance separate, pattern outliving its contents. Most stars in the Milky Way will never experience a supernova. Only stars more massive than about 8 solar masses end in these remarkable explosions. The vast majority of stars, being less massive, will instead gently shed their outer layers and fade as white dwarfs. Our Sun follows this gentler path. Most stellar deaths are subtle transformations, not explosions. Endings can be quiet, fading rather than bursting, stillness rather than drama. The Milky Way contains vast quantities of complex organic molecules in interstellar space. Molecules like methanol, ethanol, and even amino acid precursors exist in molecular clouds. Over 200 different molecules have been identified, including some with over a dozen atoms. The chemistry of space is richer than once imagined. The building blocks of life exist throughout the galaxy, suggesting life's ingredients are common. The universe is a vast chemistry lab, creating complex molecules in the cold darkness between stars. The galaxy rotates once every 225 to 250 million years at the Sun's distance. In the time dinosaurs evolved and went extinct, the galaxy completed less than one full rotation. Continental drift, evolution, the rise and fall of species, all occur against the backdrop of the galaxy's slow turning. Our brief human history occupies a tiny fraction of one galactic rotation. We are flickers in galactic time, brief moments in a much longer story. The Milky Way's current gas reservoirs could sustain star formation for approximately 5 to 10 billion more years under current conditions. However, the upcoming merger with Andromeda in about 4.5 billion years will dramatically alter this timeline, likely triggering intense bursts of star formation as gas clouds collide. After the merger, star formation will gradually cease as gas is exhausted or expelled. The era of active star formation is temporary on cosmic timescales. Even galaxies grow old, their bright youth fading into a dim future. Black holes in the Milky Way warp space-time around them, bending the paths of light and matter. Near a black hole, space curves so severely that all paths lead inward. Light itself cannot escape from within the event horizon. Time dilates, passing more slowly near the black hole than in distant regions. These effects have been measured for Sagittarius A star. Gravity is not a force pulling, but rather the curvature of space-time itself. Mass tells space how to curve. Curved space tells matter how to move. The Sun is enriched with elements from previous generations of stars that lived and died before the solar system formed. Carbon, oxygen, iron, all forged in stellar cores and scattered by supernovae. We are made of recycled stardust, atoms that once burned in other suns. The matter in our bodies has been through multiple stellar generations. We carry within us the ashes of long-dead stars. We are the universe examining itself. The Milky Way appears as a band across the sky because we view it from within the disk. If we could view the galaxy from outside, we would see a beautiful spiral pattern. From our embedded position, we see the disk edge on as a milky path. Ancient cultures worldwide created myths about this band of light, not knowing it was countless distant stars. Our perspective shapes what we see. We are part of what we observe. Insiders looking out. Stars in the Milky Way are born from clouds and eventually return their matter to those clouds. This cycle has repeated countless times over the galaxy's 13 billion year history. Each new generation incorporates elements from its predecessors. The galaxy recycles itself, matter flowing from gas to stars, to remnants, to gas again. Nothing is truly created or destroyed. Everything transforms. Matter returns, beginning again in different forms. The Milky Way's oldest stars orbit in random directions, while young stars follow orderly circular paths. This reflects the galaxy's evolution from a chaotic early state to its current organized disk. Old stars remember the turbulent youth of the galaxy. Young stars know only the current calm order. Age is written in motion. The galaxy has settled with time, its wild youth giving way to structured rotation. Even galaxies calm with age. The Milky Way contains stellar graveyards, regions where compact remnants outnumber living stars. In the inner galaxy, billions of years of stellar death have created vast populations of white dwarfs, neutron stars, and black holes. These dense objects orbit invisibly, dark remnants of stellar lives that ended long ago. They outnumber living stars in some regions. The galaxy is not only a place of creation, but also of quiet endings, accumulating its dead over eons. The Milky Way's structure constrains the possible existence and distribution of intelligent life elsewhere in the galaxy. The inner regions, with higher radiation and stellar density, may be less hospitable. The outer regions have fewer heavy elements. Habitable zones might exist, in a galactic Goldilocks zone. We reside in such a region, safe from the center's challenges, enriched with enough heavy elements. Perhaps life arises in specific galactic neighborhoods. Location matters even on galactic scales. The night sky we see is a time machine, showing stars as they were when their light began its journey. The galactic center appears as it was 26,000 years ago. Distant stars show themselves as they were centuries or millennia past. We cannot see the galaxy's present state, only its layered history. Looking outward is looking backward. The present moment extends only to our immediate surroundings. The rest is history, arriving at the speed of light. Even the Milky Way itself is temporary, destined to transform into something new through its eventual merger with neighboring Andromeda. The galaxy we call home has existed for 13 billion years in roughly its current form, but that form will change. Galaxies, like stars, like planets, like all structures in the universe, exist in states of continuous transformation. Nothing remains static forever. What we see now is just one phase in an endless cosmic evolution. Our galaxy continues its journey through space, moving toward the Virgo supercluster. This motion will continue for billions of years, carrying us through cosmic voids and toward distant galaxy clusters. The Milky Way travels through the universe like a ship through an infinite ocean. Our galaxy's voyage began 13 billion years ago and will continue long into the future. We are passengers on this galactic vessel, sailing through the cosmic sea toward unknown destinations. The Milky Way reminds us that we are both small and significant. Small, one planet among billions, orbiting one star among hundreds of billions. Yet significant, conscious beings able to comprehend the galaxy that created us. We can map the Milky Way's structure, calculate its mass, predict its future. We are the galaxy becoming aware of itself. Tiny, yes, but aware, conscious, thinking. That means something, perhaps everything. And so, our quiet journey through the Milky Way comes to a gentle close. We've traveled from the supermassive black hole at our galaxy's heart to the scattered stars of the outer halo, discovering along the way that our home galaxy is both unimaginably vast and intimately familiar. From ancient globular clusters to newborn stars wrapped in glowing gas, we've glimpsed how the Milky Way is both ancient and continuously renewing. The Milky Way reminds us that we are woven into something far larger than ourselves. Much of the galaxy's beauty happens in silence, stars being born in dark clouds, black holes warping space-time, matter cycling through generations of stars. The galaxy teaches patience, showing how meaning unfolds over billions of years, how complexity emerges from simple beginnings. By pausing to notice, we glimpse the extraordinary in the ordinary. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity, of every atom, every event, every moment in the universe. You are not separate, you are a link in the endless chain. Think about the unity of every atom in a black hole, where all boundaries dissolve, light, matter, time, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the soft gravity pulling you into sleep. Prepare for deep sleep, no boundaries left, only peace. If this gentle journey through the cosmos brought you peace tonight, and you feel moved to share it, perhaps pass it softly to someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of the Milky Way to fade now, like stars disappearing at dawn, leaving only the gentle quiet behind. Let your breathing deepen. Let your body feel heavier, as if the galaxy's gravity itself is pulling you softly downward into comfort. If sleep comes, let it carry you like a slow drift through intergalactic space, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the Milky Way will still be there. The stars will still be turning in their ancient orbits. But tonight belongs to stillness. Rest well, fellow traveler of the cosmos. And remember, you are made of stardust, and to stardust you peacefully return, if only for these hours of sleep. Fall asleep to gentle facts, dream deeper with bedtime science. Good night.